In the previous video, we discussed the current definition that we know for defining sine, cos, and tan, and that is the Sohcahtoa definition, where we manipulate the ratios of the sides in a right triangle in order to find sine, cos, and tan of our angle theta. Now, we also discussed the limitations of this definition, where we can only define sine, cos, and tan between a particular domain, where our angle theta is restricted between 0 degrees and 90 degrees. So at the moment we can define sine, cos, and tan between 0 and 90 degrees, or in other words for acute angles. But what if we want to define sine, cos, and tan of obtuse angles, or reflex angles, or even negative angles? You can see that our current definition is very limited at the moment. And we want to find a new way, a more general way to define sine, cos, and tan that can complement for any angle. And this leads into our discussion on the unit circle. There are two key features that define the unit circle. The first is that it is a circle centered at the origin, 0, 0. And the second is that the radius is equal to 1. So from our understanding of functions, we know that the equation will be x squared plus y squared equals 1. And this is the equation for the unit circle. Now, before diving into how we're going to redefine sine, cos, and tan using this unit circle, we have to go over a simple convention first, and that is how we define angles on the unit circle. We define angles starting 0 degrees on the positive x-axis, so 0 degrees will be here. And if we go anti-clockwise around the unit circle, this is going to represent a positive angle. So this here will be a positive angle. And if we go clockwise around the unit circle the other way, this is going to represent a negative angle. So suppose I draw in a positive angle for example. So let's draw one here. And we're going to name the angle theta. So this angle here, starting at 0, going around to our angle line, this is going to be theta. And we're going to name this coordinate generally as xy. Now we have all the tools to start redefining sine, cos, and tan using this unit circle. Now what we're going to do is draw a vertical line down from our xy coordinate, and this is to make a right triangle. Let's now fill in the sides. So starting with our adjacent side, this will be of length x, being the x component of our coordinate, and the height of our triangle, our opposite side, will be of length y. So again, if we go right x and up y, we'll get to our xy coordinate. And now for the hypotenuse of our right triangle, this is the radius of the unit circle. And remember, by the definition of the unit circle, the radius is equal to 1 unit. And now that we have a right triangle, we can go back to our Sohcahtoa definition to define sine, cos, and tan of our angle theta. And so let's start with sine. We know that sine of theta is equal to opposite over hypotenuse, which is equal to our opposite is y, divided by our hypotenuse, which is 1. And if we simplify, we find that sine of theta is equal to y, which means that the y component of our coordinate is actually equal to sine of this angle theta. And now let's do a similar thing for cos. So cos, we know, is equal to the adjacent side over the hypotenuse, which is equal to our adjacent side is x, and our hypotenuse, again being the radius of the unit circle, is 1. And now by simplifying, we find that cos of our angle theta is just equal to x, which means that the x component of our coordinate on the unit circle is actually equal to cos of our angle theta. And now finally, let's do the same thing for tan. and we get that tan of theta is equal to opposite over our adjacent side, which we know the opposite is y, divided by the adjacent side, which is x. And we've already found what y and x are. We defined y to be sine of our angle, and x is actually cos of our angle. So let's make this substitution, and we get tan of theta is equal to y, which is sine of theta, divided by x, which is cos of theta. Defining sine, cos, and tan in this way is much more powerful because it complements for angles beyond this domain of 0 and 90 degrees. So let's test some values. We'll test some simple coordinates. Let's start with this one here on the positive x-axis. We know that this coordinate here will be 1, 0, as the radius of the unit circle is 1. And what if I asked you what angle this produces? Well, remember by our angle convention, 0 degrees starts on the positive x-axis, and that's where we are. So we're dealing with an angle of 0 degrees. So if I asked you what is cos of 0 degrees, well, remember cos is equal to our x value, our x coordinate on the circumference of the unit circle. Well, our x coordinate is just equal to 1. So that concludes that cos of 0 degrees is equal to 1. And if I asked you what sine of 0 degrees, well, that's equal to the y coordinate, and the y coordinate is 0. And so we have sine of 0 degrees is equal to 0. And tan of 0, well, tan of 0 is equal to sine of 0 divided by cos of 0, which is 0 divided by 1, which is 0. And so we know that tan of 0 degrees is equal to 0. So it's that simple. Now let's test some other cases. What about on the other side of the unit circle? We know that this coordinate will be -1, 0. And so what is the angle that this produces? Well, starting on the positive x-axis, we're at 0 degrees, and we go around 180 degrees to get to this coordinate. So we're dealing with an angle of 180 degrees. And if I asked you what is cos of 180 degrees, well, that's just going to be the x component. So cos of 180 is -1. And sine of 180, well, that's equal to the y coordinate, which is 0. And then obviously tan is just going to be the ratio between the y and the x. And so we find 0 divided by -1 will be tan of 180, which is equal to 0. And let's test another case. So let's test down here, which is going to be 0 on the x and -1 on the y. And if I asked you what is sine of this angle, well, this angle is going around 180 and then 90 degrees more, so we're at 270 degrees. So sine of 270 degrees is equal to our y coordinate, which is -1. And what about cos? Cos of 270 degrees is equal to our x component, which is 0. And finally, what is tan of 270 degrees? Well, tan is equal to sine divided by cosine. So our sine is -1 divided by cosine, which is 0. And you can probably see here that we're dividing by 0, which in maths, hopefully you've learnt by now, is not possible. And so tan of 270 degrees is actually what we call undefined. So we can just write undefined here. And we'll discuss why this is the case later on. But for now, we can just say that tan of 270 degrees is just undefined because we're dividing by 0. So hopefully you can begin to appreciate how powerful this new definition for sine, cos, and tan really is. And let's do a couple more examples. So suppose I asked you where the coordinate at 540 degrees is. Well, we'll start at 0 degrees and we'll go around 360 degrees. So we'll end up back at the beginning, and we'll go 180 degrees more to 540 degrees. And we'll be at the coordinate -1, 0. And you could probably notice that this is the exact same coordinate from 180 degrees. And you are correct. So the values for sine, cos, and tan at 180 degrees apply to sine, cos, and tan of 540 degrees. And in fact, you can go around the unit circle forever. And so there are an infinite number of angles that apply to this coordinate, -1, 0, or any coordinate for that matter. And we can even go back clockwise around the unit circle to get negative angles. So if we started at 0 degrees and went clockwise 90 degrees, this will be -90 degrees, and we are at the coordinate 0, -1, which was the same as our coordinate of 270 degrees. And so sine, cos, and tan of -90 applies to sine, cos, and tan of 270 degrees. So that ends our discussion on the introduction to the unit circle. And for completeness, what we're going to do now is define tan in a more visual way on the unit circle, which we have not discussed yet. And then we'll do a couple more examples to finish off the video. So let's move on to representing tan in a more visual way. At the moment, we know how to represent tan as being sine divided by cosine. And this is a helpful equation, but it's also very important to understand how to visualize tan on the unit circle. And this will come especially handy when we discuss solving trigonometric equations and trigonometric identities in further playlists. So what I have here is the unit circle with an angle theta. And I've also got this red dashed line where the equation will be, because the coordinates here are 1, 0, the equation of this line will be x equals 1. And what I'm going to do is I'm going to extend the angle line on this unit circle to intersect this x equals 1 line. And I hope you can notice here that we have a right triangle. And for reference, we're going to label the corners. So starting with point 0, 0, our origin, we'll label as O. And this intersection point we'll label as P. And our coordinate 1, 0 we'll label as Q. And because we're trying to visualize tan, we can use our Sohcahtoa definition for tan. So we know that tan of theta is equal to opposite over our adjacent side. And so what is our opposite side? Well, it's this length here. And what we're just going to call it is length PQ. And we're dividing by our adjacent side. So our adjacent side will be OQ. But notice that OQ spans the radius of the unit circle. And remember, by definition, the radius is equal to 1. So instead of OQ, we can just write 1. And notice here that we have tan of our angle theta, this angle here, is equal to our height PQ. Let's understand what we've done here. So we've shown that tan of theta is equal to our height PQ when we extend our angle line to intersect the x equals 1 line. Now let's find the coordinates for this intersection point P. Well, starting with our x component, we go right along the x-axis 1 unit. So our x component will be 1. And our y component will be how far we go up along the y-axis. Well, we go of length PQ, which we've already shown is equal to tan of theta. So our coordinates here will be 1, tan of theta. And the important thing to notice is that when we extend our angle line to intersect the x equals 1 line, our y component, what we read off the y-axis, so it'll be the value here, this value, will be read as tan of our angle theta. This will all become much clearer when we do a couple of examples, but for now, let's go back and answer the question of why tan of 270 degrees is undefined. So labeling 270 degrees on the unit circle, remember we start 0 degrees on the positive x-axis and we'll go around 180 degrees, and 90 degrees more will get us to 270 degrees. So this coordinate here, which is 0, -1, is our 270 degree angle. And to find tan of this angle, we have to extend our angle line until it intersects our x equals 1 line. So if we have our angle of 270 degrees here and we extend the line, we'll have something like this. And notice here that when we extend our 270 degree angle line, we will get a line that is parallel to our x equals 1 line. And we know from our discussions on linear relationships that parallel lines will never intersect. And if these lines never intersect, then there will never be a coordinate where the y component will equal tan of our angle. And so you can see here that tan must be undefined because there's never an intersection point. It is also probably worth mentioning that any angle read off the positive y-axis will also have a tan value of undefined for the exact same reasons. So I hope you can start to see that visualizing tan on the unit circle has some benefits where we've intuitively understood its undefined values. But for now, that's going to end our discussion on this topic, and let's finish the video by doing a couple of examples to bring everything together. For our first example, we have a unit circle with an angle theta that extends to our coordinates PQ. And the first question we want to answer is, what is sine of theta? And from our understanding of the unit circle so far, we know that sine is what you read off the y-axis on the unit circle, or in other words, it will be the y component of the coordinate on our unit circle. So sine of theta, in this case, will be Q. And let's find what cos of theta is. Cos of theta is instead what you read off the x-axis, so it is the x component of our coordinate, which is going to be P. And tan, well, tan of theta we know is related to sine and cos, being sine theta divided by cos theta. And we know that sine of theta is Q, and cos of theta is P. So we know that tan of theta is just equal to Q over P. So these are some easy examples so far, but now consider what sine of 180 degrees take theta is. Well, first let's try find where our angle of 180 take theta degrees is. So remember, we start 0 degrees on the positive x-axis, and we're going to go around 180 degrees, and then we need to subtract theta. So theta is going to be about there. So the coordinate at that angle is going to be about here. And if we draw in our angle line, we have our angle of 180 degrees take theta. Remember, starting on the positive x-axis, so this angle here will be 180 take theta. So at the moment we have labelled in our angle of 180 degrees take theta on the unit circle. But in order to find sine of this angle, we have to find the coordinate here. And the best place to start is by first finding the angle right here. And there's a lot of ways to do this, but the way I'm going to do this is by considering that the sum of these angles have to add up to 180 degrees, as we have a straight line here. And so I'm going to just consider this angle to be x at the moment. So we know that x plus this angle here, which we know is 180 degrees take theta, must equal 180 degrees. And let's do some simple algebra and rearrange for x. So we can take 180 to the other side, and we get x take theta equals 0. And by taking theta to the other side, we get x equals theta. And so our angle right here is also theta. Now, if you consider these two angles as right triangles, you will notice that they're the exact same triangle, just reflected over the y-axis. And so that means that their base and the length of their height will be exactly the same. So if we consider this angle here first, we know that the base will be of length p, because our x component of our coordinate is p, and our height, the height of this triangle, will be of length q, being the y component of our coordinate. And if we reflect this over the y-axis, this will correspond exactly to our angle of 180 degrees, take theta. And so the length of our base will be of length p, but because we're reading values off the negative x-axis, then the coordinate, the actual value, will be negative p, because we're starting at 0 and we go p across, but in the negative direction. And the height of our triangle, or of our coordinate, is going to give us a length of q, for the same reason as this triangle here. And so if we label in our coordinate now for our angle of 180 degrees, take theta, our x component will be negative p, and our y component will be q, because we still go up q. And so now we have all the requirements in order to find sine of 180 degrees, take theta. And remember, the sine value is always our y component, and so our y component in this case is q. And let's do the same thing for cos of 180 degrees, take theta. And cos will be our x component, and our x component is negative p. And finally, for tan of 180 degrees, take theta, is going to equal sine of 180 degrees, take theta, divided by cosine of 180 degrees, take theta. Well, sine is just going to be q, and cosine of 180 take theta is going to be what we found as negative p. So negative q over p will be our value for tan of 180 degrees, take theta. That is the end of our first question, but before moving on to our next one, I want to point out a couple of relationships. The first being that sine of theta equals q, and sine of 180 degrees, take theta, also equals q. The other relationship is that cos of theta equals p, and cos of 180 degrees, take theta, equals negative p. We're going to cover these relationships later on, but it's good to know for now that they exist. Now let's move on to our next problem. For the final example, I want to deconstruct this unit circle that has the coordinates negative 0.17, 0.98 on it, which occurs at an angle of 100 degrees. Now the first thing I want to ask is, what is sine of 100 degrees? Well, we know that sine is read off the y-axis, and it is the y component of the coordinate on the circumference of the unit circle. So at 100 degrees, we have a y component of 0.98. Therefore, sine of 100 degrees will be 0.98. And let's do a similar thing for cos. So what would cosine of 100 degrees be? Well, we know cosine will be what we read off the x-axis, or in other words, the x component of the coordinate on the circumference of the unit circle at the given angle. So at 100 degrees, we have an x component of negative 0.17. Therefore, cos of 100 degrees will be negative 0.17. And finally, let's find the value for tan of 100 degrees. So we know that tan of 100 degrees will be sine of 100 degrees divided by cosine of 100 degrees. Well, we know that sine of 100 degrees will be the y component, 0.98, divided by cos of 100 degrees, which we found was negative 0.17, being the x coordinate. And if we use our calculator, we'll get a result of negative 5.76 for our value of tan of 100 degrees. Now let's try and represent tan of 100 degrees more visually on the unit circle, just to see if our answer looks reasonable. So we have to draw in the x equals 1 line, so let's do that now. we should remember that tan is the y coordinate when we extend the angle line to hit the x equals 1 line. So let's do this here. And if we extend this line to eventually hit the x equals 1 line, we will get a value down here somewhere. And you can see that, well, whatever we read off the y-axis will be tan of this angle, 100 degrees. And you can see that it's pretty far down the negative y-axis. And so negative 5.76 does look like a reasonable answer. Now I want to ask a bit of a different kind of question. I want to ask, what is our angle of theta when sine of theta is equal to 0.98 for angles of theta between 0 and 180 degrees. This problem is almost opposite to what we've been doing so far, where instead of finding the sine value at a particular angle, we're trying to find the angle at a particular sine value. And we also have to discuss what this domain is doing here. And so the best place to start is first realizing that sine is always what we read off the y-axis. And we know that sine, our sine value, what we read off the y-axis, is equal to 0.98. So 0.98 will be here, and we want to find what angle this occurs at. Well, if we draw a dotted line to the coordinate, we can see that this is the angle, 100 degrees, which may seem kind of obvious because I've already drawn the whole thing out for you, but we know that a solution is 100 degrees. But the reason why I chose to show this problem was because what if I go this way and reach a coordinate here? Isn't this coordinate have the same height of 0.98? Well, yeah, and that creates its own angle. So if we draw in that angle right here, we know that there's another angle that has a y value of 0.98, and therefore its sine of that angle will be 0.98 as well. So there's actually, in this case, another solution. Now all we have to do is find what this angle is, and for similar reasons discussed in the previous problem, this angle here will be exactly the same as this angle here. And to find this angle, well, we know that if we go around to 180 degrees, and the sum of this angle plus this angle will be 100 degrees, then this angle must be 80 degrees. So if this angle is 80 degrees, then so is the angle that we're trying to find. Will also be 80 degrees. And so you can see here that we have another solution for theta, where there are two angles that give the same sine value of 0.98. But also notice that we can keep going around the unit circle past 360 and get to this coordinate again, and then go around again and get to the coordinate again, which will also give a sine value of 0.98. And so this is what this restricted domain is here for. We only want to find the valid angles of theta that are between 0 and 180 degrees. Otherwise, there will be an infinite number of solutions where we can keep going around the unit circle and keep getting sine values of these angles that give a y coordinate of 0.98. And we can also go negative angles for that matter. So the domain here is between 0 and 180 degrees. Well, are these angles both between that domain? Yes, and so there are only two solutions for this problem. And now let's consider a similar problem, but for cosine of some angle theta is equal to negative 0.17 for the exact same domain between 0 and 180 degrees. Well, one solution should be pretty obvious, where we get a cos value of negative 0.17 at 100 degrees displayed by this coordinate over here. So we have a solution of 100 degrees, but let's see if there are any other solutions. So consider if I drew a dotted line down to the x-axis. We know that this value here is negative 0.17. And what if I extend this line down to hit the circumference of the unit circle again. And you can see that we have another coordinate, and this will create its own angle, where you can see that it will have the same x value of negative 0.17. And so this angle here in the third quadrant of the unit circle will actually also have a cos value of negative 0.17. And to find this angle, if we have to go around 180 degrees and we take 80 degrees to get to this angle, but if we add 80 degrees, we'll get to this angle. And so 180 plus 80 degrees will give us an angle of 260 degrees. So cosine of 260 degrees also gives us a value of negative 0.17. But our question asks for only solutions between 0 and 180 degrees. And so is 260 degrees within that domain? No, and so we can cross out this solution and we only have 100 degrees as our solution between this domain. These last two problems really show that there can be multiple angles that give the same solution for sine, cos, or even tan on the unit circle. And it is often very common for questions to ask to solve for an angle with a particular domain attached to it. And this will restrict the amount of solutions you're required to show. We will be coming back to these types of problems in a following playlist called Solving Trigonometric Equations, but I hope this gives you a good taste of what to expect. But for now, that finishes this video, and in the next video, we're going to discuss the area rule.